From the outside, this looks like just another planter, but it isn't. Inside is a custom PCB combined with hidden sensors tracking the soil moisture, temperature, and humidity of this plant.
But here's the best part. It never needs to be recharged thanks to this solar panel on the side.
This tiny 5-volt solar panel can get to its peak voltage rating using just the morning light in my room. In my last video, I explored this idea with Solar Planter V1, but it wasn't quite there yet. So instead, I made it a challenge to myself to see if I could fix it. Here's what went wrong. The main voltage regulator capped the current at 250 milliamps, which made any sort of wireless connectivity extremely unreliable. The TP4056 based solar charge circuit, being designed for USB charging, had quite a high voltage limit to start charging. This severely limited how long the batteries could charge for, since indoor light levels don't stay at peak voltage for very long. On top of that, many of the other components in the design had an unfortunately high standby current, which also didn't help with battery life. To address these core issues, I'm going to be using this. If you haven't seen my last video, then this is a fully custom dev board that I built, which combines solar charging, battery management, and the ESP32C6 into a really small form factor. The solar charging circuit is based on the much newer BQ25186, which, unlike the TP4056, is specifically designed for using a solar panel as the primary charging source. As a result, the voltage threshold is much lower, and we can utilize more of the light hitting the panel to charge the battery. Along with this new chip, the old HT7333 voltage regulator got swapped with the RT9080, which features a sufficient current limit of 600 milliamps along with an ultra-low standby current draw of 2 microamps. To even further improve efficiency, I'm going to drop the LED strip that I used in version 1. Despite only being on for a few seconds at a time, this part of the build drew way too much current and was honestly more of a waste of power than it was useful. Since the dev board is based on the ESP32C6, I now have access to the newer Bluetooth 5.3, Thread, Zigbee, and Matter connection protocols. So instead of using Wi-Fi, I've been experimenting with sending data to Home Assistant using Bluetooth Low Energy. By sacrificing range and also not needing to negotiate a connection with the router, BLE is able to bring the current draw down to just 130 milliamps. Just for context, sending data over Wi-Fi has a peak current of 280 milliamps. Zigbee has a slightly more efficient current draw than BLE, but as I don't have an existing network of Zigbee devices, I'm going to stick with Bluetooth to keep things simple. As my Home Assistant server is kind of far away, I'm also going to have to use a separate ESP32 to act as a repeater, which will relay the incoming Bluetooth data to the server over Wi-Fi. Although this isn't as clean as having the board directly send the data, the good news is that the other ESP32 can be pretty easily hidden behind some furniture. I also wanted to let you all know that I'm building a dashboard that removes all of the annoying setup for projects like these. I'm curious if other people would actually use this, so if you're interested, make sure you join the waitlist in the description. Now, let's talk about the sensors. Alongside the soil moisture sensor, I'm adding in the AHT20 temperature and humidity sensor. This lets me calculate something called VPD, or vapor pressure deficit. It factors in the temperature and humidity to tell you the drying power of the air. A high VPD means the air is very dry, which slows down the plant growth and depletes the water levels in the soil very quickly. A low VPD creates an opposite situation, where the air is very saturated, meaning that there's very little evaporation. By being able to see how fast the soil moisture is depleting, the AHT20 serves as kind of like a secondary opinion, therefore giving us more accurate data. With the electronics figured out, it was time to put it all together, starting with the 3D printed parts. If you need to get some parts of your own 3D printed, then you might want to check out this video sponsor, PCBWay. PCBWay is an easy-to-use, trusted, and affordable PCB manufacturer. Using their online tool, you can easily upload your Gerber files and choose from a variety of materials and finishes for your PCB. Alongside PCB manufacturing, they also offer PCB assembly, CNC machining services, and 3D printing. Check out the link below to learn more about PCBWay. To test out the CAD design, I decided to print with some random filament that I had lying around, as I didn't want to waste good filament on a potentially bad print. But to my surprise, this print turned out quite the opposite way, and I discovered that PLA silk is actually really beautiful. So I decided I'd use it for the secondary color of the build. However, just when I was testing out the hole sizes, I learned that this nice finish comes at a cost. To fix this, I put some heat set inserts into all the screw holes and thickened up the walls so that the layers don't crack. Wiring all of the components took quite a bit of patience due to the small amount of space, as in order to maximize the size of the pot, I had to make the sensor enclosure as thin as possible. For the pot, I went back to my trusty matte black PLA. Like everything else, this part also got a redesign, as something that I completely forgot to add in my last design was a drain. Most plant containers have many holes at the bottom, which are used to regulate the amount of moisture in the soil by releasing excess water. So I put a little cutout on the side to let extra water escape to the outer perimeter of the pot and hopefully prevent any flooding from happening. And to make the pot easily detachable, I also decided to add some magnets by pausing the print midway. And with that, here it is. To test it out, I placed the pot on my shelf and had it run for a couple of days. Alright, so I've been running it for just under a week, and here's the data. On average, it's been charging for around 40 minutes each day, which has been enough to keep the battery from slowly depleting, which I'm really happy about. Currently, it's booting up for around 5 seconds every 10 minutes to send data to the Bluetooth repeater before going back into deep sleep. And the 500 milliamp hour battery inside is big enough to keep everything running for around 2 weeks with zero solar recharging, which provides a pretty good buffer for days when there's just going to be no sunlight hitting the panel. For the sensor data, I've been mainly relying on the VPD levels as kind of a guideline for when it's best to water the plant, just because it's not considered optimal to water a dry plant when the VPD level is really high. Overall, I'm pretty happy with how everything is, but in the next version, I would most likely change this soil moisture sensor, just because from my own experience and also seeing online that they can be quite faulty and give some mixed data. I've been getting some spikes in the soil moisture. I would also change the solar panel to probably be a little bigger, just because currently it's summer and yeah, there is enough light to hit the panel and keep the battery charged, but I'm afraid that the moment that the light levels start becoming less intense, even though there will be ambient light in the room, it just won't be able to trigger the charging just because of how small this panel is. So maybe getting another panel and putting it on the side, or just getting one larger one could fix that. I would just have to wait and see. But yeah, overall, I'm really happy with it. And with that, I hope you guys enjoyed this video. I'm also really excited to announce that the Nero Studios website is finally out. So if you want to build this project for yourself or get one of these dev boards, then click the link in the description. If you enjoyed, make sure you're subscribed, and I'll see you guys in the next one.